fear of failure or being embarrassed is usually temporary. Impossible is a very foolish thing to say. Craziness really can be quantitated in terms of fundability. And that's just a way of dismissing the future rather than embracing it. Didn't consider them authorities, I consider them rebels.
Welcome to The Dish, where we invite entrepreneurs to share their insights into the next generation of biotech companies. I'm Johannes founder and CEO of LabCentral and Biolabs. After over a decade of working with entrepreneurs and supporting more than 1,200 startups, I'm here to bring you stories from our ecosystem. Are you ready to dish? Hello everyone, and thank you for tuning into the very special episode of The Dish, live with George Church. George is a pioneer of genomic science, known for discovering the first direct genomic sequencing method 40 years ago. He's a professor at Harvard and MIT and founding member at the Wyss Institute. He co-founded over 50, maybe 60 startups, 20 of them we've had at LabCentral and counting. He's named one of Time's 100 most influential people in the world in 2017. And George continues to make headlines with his work at Colossal Biosciences, aiming to bring back species like the woolly mammoth. George, what have I neglected to mention?
I think we'll get to it, maybe.
We'll get to it. Today we'll explore a wide range of topics with George on the current state of the biotech industry, as well as his vision of where the field is heading. First, typically we start the episode by asking our guests to bring an orange object. Today we are turning that around and we have an orange object for you somewhere. I think it's here. It's our orange woolly mammoth that we want to give to you as a memory for this.
That's great. Yeah. I don't have one already.
That's awesome. On the woolly mammoth theme, George, one of the things that the general public can embrace very easily is this idea of de-extinction. And I know that you have a company actually working on that,
yes.
Colossal Biosciences. Is there a timeline in which we can expect real woolly mammoths to walk the streets again?
Well, no, and no. It's not. I like to keep expectations low. It's not going to be a real woolly mammoth. It's going to be better than a woolly mammoth, hopefully, but it won't be real. We are making progress on a number of species, actually. Some of them there'll be a lot of announcements in February, probably. The timeline that the CEO set for the first engineered elephant is 2008, I think, 2028. And we have already engineered a pig with about as many changes as we would want to make initially anyway. So that's kind of a warm-up in a sense. Not at Colossal, but at eGenesis for a completely different reason.
Yeah. You have, I believe, de-extincted a species already, or a couple, right? Isn't that right?
So the goal here is to de-extinct phenotypes and ecosystems. There are two species that the world has de-extincted, and I'm actually glad I wasn't involved in either one of them. That one was a retrovirus, and another one was the influenza, 1918 influenza virus. So, and those protocols are available on the internet in case you want to do it in your home. Yeah.
Well, the woolly mammoth idea, I know, is one that is not just about a fun plush toy or a tourist attraction, but there's actually a deeper thought behind that.
Yeah, deep enough that it's hard to explain. But the short-term payoff for the company is technology development. So we're already spun off two companies out of it that are technology-based, Form Bio and Breaking. But the longer-term vision is to address climate change, at least in some small effect, in a way that it is self-sustainable, that it doesn't require heavy financial input, and that's saving the Arctic, which has deeper topsoil than anywhere else on the planet. That topsoil is full of carbon that can be released. Also, the grass is unusually productive in the Arctic, and that's why there's so deep a topsoil, but it's been displaced by trees. We're just trying to shift that balance back, and elephants are among the few species of animals that like knocking over trees. They just love knocking over trees. Look on the internet for videos of elephants knocking over trees, and you'll keep yourself entertained.
So that's the long-term view of this, right?
That's
mammoths roaming the Siberian tundra,
or at least
knocking over trees.
Cold-tolerant elephants, yes, right.
Right. That's a long-term view. You did mention eGenesis.
Yes.
It's working to solve the organ transplant shortage by engineering pigs and getting organs donatable from pigs rather than just a pork chop. We will have high-value uses of pigs.
Right.
How close are we to routine clinical use of these technologies? Xenotransplantation.
Well, yes. So you always add an adjective that makes it hard to answer the question. Routine is the adjective in this case. Real was the previous adjective.
Real.
Yeah. Everybody in this room probably knows the difficulty of doing clinical trials. We are at that point now, and we hope, like everybody does, that the clinical trials will go well. But I'm fairly convinced that there is such a need, and the technology is looking very promising so far. And we have done a few individual humans. So I think a couple of years we'll see how the clinical trials are proceeding. Yeah.
So are there additional technical hurdles that need to be addressed, or do you think the technologies that we have today will be the ones that solve the xenotransplant question?
I think I don't think they need to be addressed, but there will be a temptation to address them. So what I would say is that we hope that we have something that is sufficiently human compatible that normal immune suppressants will be adequate. So the same ones you would do human to human. Long term, we would like to eliminate immunosuppressants, which would be better than anything that we currently have. And in fact, there's many opportunities for engineering something that's better than a human transplant. It's not a promise, it's just an aspirational goal. So, but the first thing is just to deal with the tragic shortage of organs. But there's these incredible opportunities for making them better.
Yeah. So these are opportunities to help, very obvious medical need. The gene editing and engineering technologies have large potential to do good in that area, but they also often raise ethical questions, right? How do you balance the responsible use of technology with these challenges, or bring the public along when they're not quite ready yet?
Well, first of all, I don't twist any arms. I want to be ready on their own. I want to listen to the public. So we do a few things that have to do with having dialogue. So along with my wife, about 2 decades ago, we started something called pged.org. It's a personal genetics education. And we do outreach to high schools. They have lessons they can pull straight out of the web and college, and Congress, and congressional briefings, and screenwriters. And so that's one way of engaging, just and partly finding out what people want to hear. Do you want to, I think in general the public is quite open-minded to these sorts of things, at least the things that I've been working on. But almost everything that we work on, I can see, just because we're first at the scene, get to see all the positives and negatives a little further, a few years out. And so I try to accompany every new technology paper with a paper on bioethics or on safety, and And I think that helps get the conversation going sometimes years in advance of when you actually need a policy, and that's a good thing. You know, if we happen to raise a red flag, then it turns out it's not a risk. That's not a bad thing.
Yeah.
You know, to have a little extra conversation. You know.
There was a few years ago, there was this case of germline editing in human babies in China that created a huge public outcry. I think mostly because the public wasn't ready.
Right.
You actually came to the defense somewhat of the scientist.
Right.
Do you want to?
I was probably the only person who came.
Yeah.
Because there was really no percentage in coming to his defense, and I did it. You know, it was more balanced than unilaterally in favor. And even though I have spoken out on the possibilities of germline, I don't think there's a compelling argument right now for why it's advantageous over, say, somatic gene therapy or a variety of other therapies. And it has a major disadvantage in that, two disadvantages. One is the clinical trials probably take longer. You know, if you want to see if you've cured late onset Alzheimer's, then that's a 70-year clinical trial. Well, if you had a somatic cure, it could be a few weeks. And the bigger one, I think, is that there are 8 billion of us that have already missed the deadline for the germline engineering. So the market size is a little bit smaller than that.
Yeah. As an industry, we have a big stake in and an interest in having the public understand these novel technologies and not be scared of them and see them as a threat, right? Is there a way that we can help in that discussion? What do you ask people in the room to participate in that discussion?
Well, again, don't twist anybody's arm, I think would be lesson one. A lot of times when you disagree with somebody, you think that they're not thinking it through. And I think give them the benefit of the doubt that even if they're, framing it differently than you would. For example, GMOs is a classic one. I think Monsanto was very, rough-necked about it, and they could have been more embracing of their opposition. And to some extent, the opposition had a point, which was it wasn't clearly articulated in the grocery store what it was good for. I mean, was it bringing down the price? Was it making it tastier? Not really. And even if it were, it would be kind of hard for them to perceive. So if there's no advantage, then logically, there's going to be great resistance to any risk whatsoever, even imagined risk. So I think that's what we have to keep looking at, is keep very clearly articulating the advantages, and then the risk will take care of itself. Think of like cell phones. For a while, people thought it was going to melt your brain. Nevertheless, it had such advantages that all the rich folks got, big, car phones, that would carry around in their Rolls Royce, and then they'd have this big thing next to their head frying their brain. So risk it depends on the benefits.
Yeah. Yeah. Do you have in your lab when you have someone propose a new idea, do you engage in these discussions of what could be the risk of this, or we shouldn't do this because it's going to be badly perceived? Is that even
Well, we talk about the risks, so we don't necessarily talk about you shouldn't do this. It's a matter of first exploring the space. Like what are things you could do to mitigate? First of all, what are the risks? What can you do to mitigate those? What new risks are created by the mitigation of the previous risks, et cetera? And then if it seems sufficient, then we will write a paper on the risks and benefits and how to minimize them. So for example, and we do this almost every technology. When we improved synthesis by 10,000-fold, I put out a white paper in 2004 about how we could do surveillance. Up to that point, everybody was talking about voluntary, signing some moratorium or something, and I said, no, you need surveillance. And when we did gene drives for, eliminating
You have to
malaria.
explain what gene drives are.
Gene drives are just a way that you can force through a population that does sexual mating at a high rate, like mosquitoes and mice and things like that. So and you can spread a favorable trait through it, like resistance to malaria. You can have mosquitoes become resistant to malaria. Some people would like to use the gene drives to eliminate the mosquitoes, which is another possibility. But just, anyway, when we proposed that, our first 3 papers were on how to contain it and reverse it. I think that's a good way to start, rather than just being an advocate, where you seem very, the emphasis shouldn't be on selling it. It should be on making sure that people are convinced that you're at least thinking about it. You haven't thought of everything. You've thought of a few things that could make it better.
Yeah. Often, that's sort of my next question, is often the scientists, and you mentioned Monsanto as part of that, are so eager to sell their solution because they've thought so deeply about it for a long time that they're not sort of engaging the public sufficiently to address those sometimes justified concerns. And so that's one of the points that we hope for all of you to take home to help communicate about science at the dinner table. It used to be that scientists were amongst the most trusted people, and somehow over the last several years, COVID specifically, there's been a strong counter-argument that seems to revel in trashing science, right?
Yeah, well, vaccines have been unpopular since the day of Pasteur and Jenner. There were cartoons, of contemporary cartoons, where they had like little cows popping out of the skin. You've probably seen this. There's something about it. There's something about food and putting things, putting infectious agents into your body that get people's attention.
Vaccines, yeah. A hot topic in science and policymaking is artificial intelligence, and the public is wavering between unconditional trust and using this and fear of the damage it could cause. How do you see AI supporting biotech and bioengineering in our world?
Yeah, so I've been working on related topics for a long time. And of all the different applications of AI, self-driving cars and chatbots and hallucinations, I feel that the best application so far has been protein design, a very specific part of biotech. I think there are plenty of other ones that we won't be dismissive of, but that has really resonated. In fact, I think 5 of my startups, 4 of them are here. We're involved, Nabla, Jura, Manifold, Shape, and Dino, all really did this interesting combination of machine learning with multiplex libraries, maybe millions, billions, and just Jura and I just published one preprint on libraries of 10 to the 17th. So this combination of big libraries with machine learning is incredibly more powerful than the 2 separately. So I think that's a big payoff. I am concerned about some of the other applications. Again, the benefit to risk ratio is not in the right place. And I think there's a tendency to say, oh, we need $1 billion now or $1 trillion now and they're creating an artificial crisis. There is no crisis of lack of AI. We're hypo AI. It's a fake crisis. Although it will become a real crisis if we keep going into it with uncritically.
Yeah.
And there should be more emphasis on containment. But anyway, I think applying it to protein design is fairly safe for now. Although David Baker and I did just write a paper in Science about how the problem of AI protein design is related to the thing that I wrote about in 2004, which has the same solution, which is surveillance of all synthetic DNA.
Is AI going to replace science?
Well, it's part of science. I mean, it's already, I mean, computational tools that are very similar in outcome. I mean, we were designing allosteric proteins, which are actually harder than designing antibodies back in 2015. It will be part of science. Will it replace scientists, I think is your question, rather than science.
Key question. Will it replace lab space?
No. Like I kind of answered that question, preempted that question by saying the thing that's powerful is ML plus ML, machine learning plus mega libraries. And I think that will remain the case, is these large libraries allow you to do things that are exactly accurate, as opposed to some approximation, in the sense that we can inject millions, possibly billions of different therapies that are barcoded and do them and study kinetics and tissue specificity and toxicity all at once. So in an expensive primate, instead of doing 1 million primate experiments, which would probably break most of your budgets, you can do one. So I think experiments, but still AI could take our jobs in running those experiments, or they could say, I got a primate, Instead of being a scientist, why don't you be a primate,
I think it's safe to say that...
That's a bright idea that AI might come up with, yeah.
That we will see a massive acceleration of productivity or increase of productivity, right, through these tools.
Yeah.
And I think that's to the benefit of
the future
everyone.
is hybrid.
Yeah.
So we're all kind of hybrids because of our cell phones and things like that. But
we're
going to be even
bigger
time hybrids, yeah.
I often say to people that I think our 21st century is the century of biotechnology. We see it here with high-value applications in therapeutics, but we have the tools to do many other things. And I believe that we will see biotech and synthetic biology applied at much larger scales. I know that you often talk to that topic. Where do you see the application of biotech in this decade, in this century, and at what scale?
I've got an easier question, which is, where won't we see it?
Okay.
I think almost even things that are solidly in the inorganic physics category can have a biological component. It's even possible that AI will become natural intelligence again, because there's a lot of things that the human brain does quite well. And if we started engineering it the same way we engineer, I think right now AI is convenient in the sense that there's no IRB approval for messing around with the AI brain. And there's quite a bit of challenge to doing that in the human brain, but I think that one of those two will change with time, or both. So, yeah.
What are some examples where we could see synthetic biology used at large scale, maybe outside of the therapeutic or those medical fields that we do here at LabCentral?
Yeah. I mean, one thing to start with the most far-fetched thing, and we can come back a little bit down to earth, but I think that synthetic biology could be used to make self-replicating systems that assemble large complex objects, like, say, space colonies. You could send a very small package that then, if it knows how to, and again, it would be a hybrid, some kind of inorganic, organic biology hybrid. And those can be sent very inexpensively. I even published a paper on how you can send things at relativistic speeds, because the light sails are so tiny they don't require the kind of investment that you have in the breakthrough starshot even. So that's far-fetched, but it's an example. I think that almost the thing that's beautiful about biology is it's already solved the problem of the race to the bottom, where you have atomic precision. While we wax very enthusiastic about AI that's based on NVIDIA chips, where the feature size are getting down to, quote, 3 nanometer, which is really more like 30 nanometers if you count all the wires and everything. And biology has been sub-nanometer forever. And we're just harnessing that. We're learning the language of protein design for sure, and developmental biology soon.
So developmental biology and self-assembling systems.
Right.
That's hard for many of us to follow and understand. What is the more 10-year out, maybe not 50-year out, big thinking that you enjoy?
Yeah, you didn't specify the timeline.
Yeah, okay.
It's going to be here on Friday, 50 years from now, right? Yeah. I think this revolution in protein design is going to affect everything. Just imagine that you have, right now you can order up a piece of DNA that will hybridize to any other DNA or RNA you want, just from first principles. We'll have that same ability with antibodies. And more importantly, antibodies are kind of like, I call them rocks. They kind of have one configuration, but allosteric proteins, we've done those. Done capsids, which are very dynamic things. They package, they find the right place, and then they unpackage, and they do and so I think that's going to allow us to do all kinds of atomically precise things. You said non-medical, including materials, making new materials, smart materials, new kinds of computers, hybrid computers that have the advantages of neural systems, and real neural systems, not silicon neural nets. So.
Computers, biologic computers.
Hybrid, biological and electronic. Whatever, you might make the electronics by biotechnology, because it's, the problem with using dopants in standard silicon is that if you get to a certain size, they become the random Poisson distribution is no good. But if you actually engineer the exact position of everything, you can do all kinds of cool things that you can't do with statistically heterogeneous.
And genetic engineering to be used to address environmental challenges and climate change and pollution. Yeah. Are you working on solutions there? Are you seeing, you mentioned the woolly mammoth, that's one sort of ecosystem scale solution. Yeah. What are some others that you?
Yeah, so we want to, among other things, we want to be able to sequester carbon. We want to do bioremediation. This is, probably involves genetically engineered bacteria or elephants, and it's totally feasible. And I think the reluctance we had for going to the grocery store for GMOs, where there was no payoff, here there's big payoff, and some of the Europeans who are most vocally opposed to changing the grocery store are very much in favor of it when it's talking about climate. They've embraced climate change much faster than we did, even though we might have, few individuals in the United States might have raised the flag, I think Europe. And so it's surprising to hear them supportive of possible GMO solutions to endangered species, to restoring ecosystems to a more carbon sequestering form.
What form will that take? Is that algae? Is that engineered trees that capture more carbon per year? Or
yeah, well, so different environments have different answers. Some cases you want more trees. In the Arctic, you probably want fewer. There's some plants that grow very quickly. There are some we just discovered a few cyanobacteria that have a record for growth rate, so that photosynthetic at 90-minute doubling time. And we also have worked on the fastest heterotroph, which is 15-minute doubling time. If you think of that the way you would think of a cornfield, think of the cornfield turning into 2 cornfields in 15 minutes. I mean, that's a mind-boggling thing. So I think if that can be, and we're trying to harness that into something that fits in your kitchen, because if it's really 100 times more productive, might be 100 times smaller. You just need an abundant source of energy, and I think we're getting that. We're taking solar much more seriously than ever before. Geothermal, even fusion might be around the corner. The point is, if we have abundant energy, we want to trade it off into things we really want, which is eliminating supply line fragility. We want to have, convenience, programmability, things like that. So instead of sharing, we'll be sharing recipes on the internet, but in a whole new way.
Yeah, make it in your kitchen.
Yeah.
In your lab, you attract some of the smartest people in the world. They come up with very creative, sometimes maybe wacko or crazy ideas. Yeah. What's your process of going through with them about what's feasible and what may be feasible only in the future, or we call it wacko today? How do you go about that?
Well, I don't want to lay all the blame on them. I am occasionally responsible for some of the crazy ideas as well. But yeah, I think we have it helps to have a track record. It's like when I first started the lab, nobody would work on the projects I wanted to work, because they just sounded crazy, and they just felt like, we'll take the money and run, and we'll just do whatever will get us paper. And with time, it became evident that it's almost exactly the same effort to do something that's mediocre as to do something that's very challenging, because to some extent the publication bar is a little lower if you're doing something that everybody thinks is impossible, and you do anything at all, they give you a paper. So yeah, we try to de-risk it to come up with intermediate things that are not only publishable but actually useful. So it used to be, when I was a student, it was the case where you had to choose whether you were working on something that was, very basic and basic science and inapplicable to anything, or versus something that was clinically or otherwise societally applicable, or a technology. You had a 3-way choice, and now we insist on having all 3 of them. That's the entry. So if a crazy idea has those 3 in common and doesn't defy any laws of physics, then it's actually surprising how quickly it comes when you just put it in purely engineering terms. If you require new science, or in particular new science contradictory to current science, then you got an indefinite amount of time. But if it's just engineering, like when we put our mind to nanopores, that was fairly quick. The CRISPR was alarmingly quick. We published in January, and by April there were 10,000 requests for plasmids at Adgene. And next-gen sequencing arrived as soon as we got rid of the Genome Project, which had a love-hate relationship. I helped start it in '84, but they never got serious about technology until it was done in 2004, and then boom, next-gen sequencing just took off. Yeah.
When you recruit people into the lab to come up with these ideas, or maybe challenge you on your own crazy ideas, you've said in one of the interviews that I saw that you select for niceness in your people, which resonates with us. I think we have at LabCentral, we have a similar value in our value description there. Can you tell us a little bit about that and why it's important for your lab?
Well, I think it's important for everybody's lab. There's just, and I think there's a general trend.
But it's not an emphasis in most.
Yeah, that may be. I hope that there's a general trend. It's like Steven Pinker has documented there's less violence in the world. I think there's more niceness, but not everybody has gotten the memo yet. But the part of the reason that I like putting that higher on my interview list, is than say genius, is that I figure if they can't be nice, and I insist, it's one of the few rules I have in my lab, is they need to have a buddy. It's a buddy system, at least one person in the lab that you can imagine co-authoring a paper with, or hanging out, all day side by side on the bench. If they can't be nice to the person sitting next to them on the bench, it's unlikely they're going to have the right mindset for helping the world, which is one of the things that we aspire to do. It also it just makes for a more pleasant work environment. It seems obvious, but yeah.
You've had a hand in helping start over 50 companies. What's your decision framework for commercializing? And what's the process in your lab that allows you to winnow ideas? I'm sure that all of your grad students and postdocs are now coming and they see the tracker and say, I want to be a founder of a company, but not all do get there. So how do you select?
Yeah, so some of them, yeah, I think increasingly the beacon draws them in, and then it's nice to have expectations aligned with what's possible. Some of them don't realize, some of them realize that they aren't going to necessarily be their idea may not make it, but they're happy to join somebody else's idea in the lab at the time. You know, it's more about timing. If their idea is 5 years out, then they'll just say, I got to end my postdoc now and work with this other team that's 1 year out, and then they'll get around to their 5-year thing eventually. I think it's fairly evident, I think, even to inexperienced postdocs, what's feasible and what's not. I think when they come into the lab, if anything, they see they reset what they think is feasible. In other words, we don't allow the word impossible in the lab at all, but they can see in terms of what can be done in a short period of time. We have kind of a track record of doing things in short, and we pick topics that look impossible or very, very hard, but we know that they have a good chance of being easy, and rather than throwing ideas into the trash, we put them up on the wall. It's like, here's something we can keep looking at from time to time and see if something we just invented might reflect on something that we did consider very hard. So we're always looking for that kind of opportunity. It's not that, there are very few things that require absolute rejection, and the prioritization seems to be pretty, you know, you get lots of feedback too. As soon as you start trying to get an investor, you realize that maybe it's totally feasible from your technical viewpoint, but it's not feasible from a investment viewpoint. And also we have, because they were nice and previous generations that have succeeded at places like LabCentral, they come back and they tell people, they give them a better feeling and better intuition for what's feasible. Yeah.
So of your 20 companies that have, of your many companies, 20 have been there, and I think we have a list of the many names up here. I'm sure some of you know them. What makes them come back here, or what do you like about LabCentral? Let's put the words in your mouth.
Right. Well, obviously that, yeah, we're voting with our feet. You know, they, like I say, they're not just, they're friendly to next generations. They tell next generations where the potholes are, where the barriers are, and so they must have told them what was good about LabCentral, and I think it's a great way to get started without, you know, removing a lot of the friction, a lot of the learning curve, and so forth, and you know, they don't stay here that long. You know, it just doesn't take that long to get up to speed, and then it's make room for the next set.
Yeah. Many of our founders that we've had out of your lab were first-time founders. Yeah. They came here as academics, first time in charge of a company, and that's a big reality shift that they have to go through. Yes. How do you prepare them? What are the biggest challenges that you see? How do you prepare them for that?
Well, it was a reality shift for me to see that, because I had the mindset. You know, I had my advisor Wally Gilbert started Biogen just down the street, and I was one of the first employees there for a few months, and I was used to the idea that you need a great deal of experience to be a CEO. In fact, the ideal is to get a CEO that's already successfully done maybe gotten a few things into clinical trials. And so my advice, my poor advice, was that, you know, you really shouldn't want to be CEO, and maybe you even should question whether you want to be CSO. But CSO seemed reasonable. anyway, they proved me wrong on that. And now it's almost the only way we do things, is that postdocs become COs and CSOs and CTOs straight out of the lab. That they pick up a little bit by watching their colleagues that are a year or two ahead of them. They watch how that goes, and they keep talking to them. And that probably is better training, or is adequate training. I'm not going to diss the Sloan School or Harvard Business School at all. They're my friends. I teach there. But this is another way. It's another way.
Are there courses or classes or things that institutions can offer to get scientists more ready for this transition?
Absolutely. I mean, we have combined Harvard Business School and School of Public Health and medical school and so forth. It's up to them. Sometimes they're in a big rush to go, they've already spent, all these years in college and graduate school and postdoc. But the business school programs are not that long. It's a fairly good investment, but very few of them have done it. I mean, I certainly haven't tried to talk them out of it. After I gave up talking them out of being a CEO at all. I taught some classes with Vicky Sato, and I teach some other ones at the business school. There obviously is a lot of energy and enthusiasm in those courses, and you meet people, even if you don't learn a single thing in the classroom, you meet the next, but you also meet them here, right?
I'm even thinking about like pre-business school, right? Like when you become a chemist, when you become a biologist, is there use in exposing them to this world outside of academia? Or do you see it as a distraction?
No, they are definitely exposed to it in my lab, and I think it wouldn't hurt to have it in other labs. I mean, there is a certain concentration effect. There's one human urge, which is distribute everything equally in every congressional district. And there's another urge to focus everything in Boston and in San Francisco, and in LabCentral, the center of the universe. But you don't want to go to black hole density, but you want, this is a good density,
Well, we are all here to learn from you today. And a question that I was prompted to ask you is, who do you learn from? Who is it that you look up to? Who do you read? And should we learn from the same people?
Yeah, I mean, I think I mainly learn from my students and certainly colleagues. There's diverse sources. Oh, and AI, obviously. Yeah, they wouldn't let me get away with not saying that. When I was young, I couldn't read very well. I was dyslexic, mostly over that. But I did march my way through biographies of Luther Burbank and George Washington Carver and Madame Curie. And those were kind of, I'm not sure exactly what I learned, but I learned that they, it started me undermining my respect for authority. I mean, I didn't consider them authorities, I considered them rebels for some reason. And so that was part of the learning. But yeah, I think we all have many, many different mentors, some of which wouldn't be described as mentors, but they're sources of inspiration.
I like the learning from the students.
Yeah.
Point
definitely.
We have that a lot here with learning from our entrepreneurs and our distributed effort in science.
I think they see the future very clearly, sometimes distorted, but there's a creative source there, yeah.
From looking back at your founding many companies and supporting many entrepreneurs in founding their companies out of your lab, is there key advice? What advice would you give them as they start out their journey?
I probably give this out all the time, but I'm not sure. I would say, first thing, don't worry about being first. Being second's not bad in the business world. The first one gets to find all the landmines, and which is usually fatal. And often the more cautious investors want to catch up, and so they'll give you a little bit more than they gave in the first round. So don't worry about being. And I think that applies in academic publishing as well. There's a lot of panic about being scooped, and I think what's better is to be right than to be first. So you have a chance to do better. What else? Build a good team. If you get one bad apple at the beginning, when there's only 3 of you, it's very hard to recruit the 4th person. But moreover, on the more positive side, if you get right energy in the room, you can do amazing things with a team of 2 or 3 people. It's just absolutely amazing. So I could go on, but gives you some idea.
That's great. Team, we love that. No fear of being second is a great one. I think we have a few minutes left for audience questions. I know that there's an online tool where you can submit some questions for George. And also we have a very highly qualified audience here, so I'll open it up for you, for your questions.
Wonderful to hear the presentation. I'm actually just curious about some of your crazier ideas. Love the concept of, from an AI approach, really combining machine learning with the mega libraries, and think about some recent advances in quantum computing. And so for you, like, what questions today are kind of answered with the computer power that we have? And what are some of those crazy questions that you really need from an engineering aspect to address?
Yeah, well, quantum's an interesting case because there are things that you can build if you have atomic precision, like super coherence, that's very hard to build with nanofabrication technology, micro and nano. That's one example. Another example, I think, we don't usually think of these as quantum computers. Quantum computers, they have to be qubits. It's because we're so enthralled with the von Neumann architecture that it has to be digital and has to. But the qubit, I mean, and we also get very obsessed with breaking security codes, like breaking RSA with quantum. But one thing that quantum does extremely well is it's the perfect simulation of itself. So that's why I think libraries, in a sense, are a quantum computer. We just don't appreciate it. If it doesn't fit into a qubit, then it doesn't compute. But in fact, if I can build 1 million viruses for gene therapy, and then put them into a primate, that's the perfect. You won't come up with a better simulation with von Neumann or quantum computers, but they could be. And in fact, yeah. So if you want to know how things interact with the immune system, the liver, and all this stuff, even organoids aren't a good enough system, much less something that happens in silico. So I'm not saying this will never be the case. I'm just saying right now, that's a quantum computer. There's actually a field of computing that people hardly ever, you can find it in Wikipedia, but you hardly hear it, which is natural computing, where if your ability to make a system is cheap enough and fast enough and scalable enough, then that actually is the most efficient way to compute it. And so you could think of, if I have 2 black boxes, one of which is a supercomputer that's using 200 kilowatts, but you don't know that, and the other one is the actual thing that it's trying to simulate, do you really care what kind of computer it is? I mean, I think we need to broaden our mind as to what a computer is. Mm-hmm.
Thank you. It's a real treat to listen to you tonight. I myself, and I think probably quite a few people in the audience, have had moments in our research career where we think of something, and if somebody, obviously it's crazy, you get laughed out of the room, or maybe we don't really know what something could be used for. And then 15 years later, all of a sudden there's that moment and we just think back to, wow, I remember being in that room and getting laughed out of. And I'm curious for you, are there some moments and standout ideas that sort of resonated like that, like in your history, like what stands out as moments like that?
Almost every moment. But yeah, I mean, there were definitely, I think when I first proposed nanopore sequencing at a DOE meeting in Santa Fe in, I don't know, 87 or something, the guy after me, we used transparencies back then. You know, some people use slides, but transparent. And he drew a picture of DNA with a little a nano-fabricated A sticking off of it, and then a little T. And his idea, and he was making fun of my thought that you could use single molecules to essentially image DNA as it's going through a pore. And he, I mean, I just thought it was so ridiculous it was worth making a joke. And I think I took it well. But that was just the beginning of the criticisms of nanopores. And there was a time where where both PacBio and nanopores were being severely criticized because they had incredibly poor error rates. They had like 10% error rates, right? And in fact, the investors were saying that we're starting to sue the company for misleading them. And I remember, I mean, I had equity too, and I said, they very clearly stated it was 12% at the time that you made the investment. And so, and the list goes on and on. I mean, you know, even before the nanopores, I had become infatuated with sequencing all the people on the planet. This is like when there were 6 billion of us rather than 8 billion of us, and that was considered complete Looney Tunes. And so when I would say I thought that we could I took it in small steps. I said I think someday we'll be able to sequence a bacterium in 1 year, and so they started making fun of me. That, oh, he's going to sequence the bacterium next year, and it's like that's a different statement, right? And that's just a way of dismissing the future rather than embracing it. And now, if somebody said, it took me a year to sequence a bacterium, they'd say, what's wrong with you? You know, we did 100 this afternoon, right? So, you know, I think the thing is I think I fortunately had fairly thick skin and a good sense of humor. I sort of felt like, well, you know, I'm going to accumulate. I'm going to make a list of, you know, all the predictions of what is impossible. Impossible is a very foolish thing to say publicly, because, unless you have really good physics behind you, you know, like speed of light and Heisenberg. It's probably going to be not only possible, but it's going to be highly desirable and arrive ahead of schedule. Almost everything seems to be arriving ahead of schedule now. So, but thanks for the question. It's good to get that one out. You know.
I'd like to ask a little bit more about maybe how you encourage sort of roundness and creativity in the students that you bring in. You talked a little bit about niceness being more important than genius. We've talked about sources of inspiration. What does your practice of creativity look like outside the lab? How do you encourage maybe a similar practice in your students?
Yeah, great question. I think, you know, I think in our environment, you know, we're very privileged. I'm sure everybody in this room feels that way. I think there's a lot of creativity, but I think there's also a great tendency to trash that creativity. In other words, almost everybody, you know, it's like you said, you have this great idea, and you're either laughed at or you're afraid of being laughed at, and you just say, I'm going to throw it in the trash faster than anybody else does, and that'll be my success. And so in my lab and in my ecosystem, I try to say, look, the problem isn't failure, right? Embrace failure. So you have different metaphors, like there is the NASA or the metaphor, which is failure is not an option. That was their motto. And my metaphor is mega libraries again, is we got 1 million things in this library, and probably at most 2 or 3 or 4 of them are winners. And so why do we worry if we fail a million times? What's important is trying to find that winner. And so I think if you take that on in your personal life, not just in your scientific, or your personal scientific life, I think that helps. It's just fear of failure or being embarrassed it's usually temporary, right? So yeah, I think that helps. And the students pick that up. They pick up even body language. You don't have to even say it. If your body is leaning towards the trash can, that's a different one than putting it up on the wall with a framer on it, right?
I think that's so important also for entrepreneurial experiments, right? Like I often see this in, like, I think the US is super permissive in taking entrepreneurial risk. Yeah. It's sort of built on this concept. But I'm from an old world country, and we work a lot with Japan and Germany and all of these where failure is not such a great option. Yeah. And so I think that mindset is so helpful and certainly important for entrepreneurs.
Yeah, I say if you're not failing, you're not trying.
Yeah.
I completely flunked out of graduate school, so I had to repeat 9th grade as well. So I think those early experiences made me less worried about failing. Yeah. Because America is a good place to fail if you're going to fail. Yeah.
Yeah, because it's accepted that you learn your lessons in that, right?
Absolutely.
Thank you very much. Really inspiring talk. George, you're one of the very few people who is a busy professor at Harvard and MIT and other places, and set up the 50 companies. How do you manage that? Do you have like a business partner that handle a lot of mundane things that are associated with setting up the company and renting the space and track the finance? How do you manage so many companies and leading academia at the same time?
Yeah. So I think you hit the nail on the head in that I do have partners. I'm not sure I'd call it mundane. I certainly don't want to dismiss. They may consider what I do mundane, so we're even. But yeah, I do almost no administrative stuff at my companies or in my lab, and I'm not proud of that necessarily. I'm just not competent. So I have maybe half dozen people at Harvard. I have helpers always. Like LabCentral is an example. I mean, I don't have to do all the things that they do here because they already do them. And so I think some people can't acknowledge their limitations. I think that's something that's good to get used to. Is you can't do everything, one solution is you just do one thing. Another solution, I'm not satisfied. I like doing a lot of things. I'm just maybe ADHD, but I like. But if I admit that I can't do every aspect of it, like the legal and the various administrative things, then people will be happy to join and help. So yeah, the answer is I don't do everything, but I do enjoy the diversity of science. I'm a science engineer 98% of the day. That's what I do. Yeah.
Jay gets the last question.
Oh, thank you very much. The Center of Universe here, LabCentral. We are struggling these days with all these challenges of fundraising. So from your mega library of 50 plus companies that you created based on many different sciences, some of them probably had easier time of getting fundraising, and some of them had difficult time. Yeah. So my question is, do you believe investors, those venture capitalists, do they get it right to invest in the right science, or do they tend to invest in wrong sciences? So if I'm not getting good investment Is it my science problem or is it their problem?
It's definitely not your problem. I try not to put it at their feet either, in the sense that, fortunately, there's not one investor, right? That, you know, if we had a great dictator investor, that would probably be anti-innovation. And so, you know, I found, you know, I get lots of rejections, and my teams do. But fortunately, there's a lot of different ones. So for example, there was one company or one idea, one crazy idea that I thought was my least fundable idea ever. So you know, craziness really can be quantitated in terms of fundability, and that was this idea having to do with elephants. And I got a little bit of money from Peter Thiel, I don't know, maybe 2 decades ago. And we stretched it out over, you know, life support, and we would get, you know, volunteers that would, you know, be working in the, you know, Biotech Valley here, and they'd come in on weekends and nights and work with us. That's how we were funding the mammoth experiments. And I thought, I was so sure it was unfundable. This is one of my many mistakes in life. I didn't ask philanthropists or government or investors. I just felt it was just something we would do in our spare time, and maybe someday it would become more feasible. You know, that's one approach, to just keep it on the back burner until, and it started before we really had, it started 5 years before we had CRISPR, for example, and CRISPR has been very valuable for engineering the pig and the elephant as well. And so you keep it alive for a while. And then Ben Lamb showed up with no agenda, just wanted to learn more about what was going on in my lab, kind of like what's going on right here, just random questions. And then as I'm randomly walking through the projects, he said, stop there, you know, elephant, tell me more. And he says, I'm going to go out and raise you $2 million. And I said, no way. I mean, it's, you know, I've been running on $100,000 for the last 2 decades. And he said, yeah, I'll try. And he didn't promise. He just, I'll try. And he went out and he got $225 million. So he missed it by 2 zeros, yeah. And he's still raising money. That's, there's a lesson there somewhere. But I think the point is, it's not, the investors aren't wrong and you're not wrong. It's just there's a lot of diversity, fortunately, out there. Same thing goes for grants. There's some grants I no longer qualify for because I got too many of them. Go figure, you did too good a job and you get penalized by not qualifying for the grants anymore. But that's not true in the VC world. The better I do, the easier it is I don't have to struggle quite as much as I used to, yeah.
I think that's a great take-home for Jay. It's not you, it's not them, it's the diversity. Thank you so much, George, for joining us today.
Yeah.
And it's been such a pleasure talking with you, and I'm sure we all leave inspired from your ideas and your experience. Yeah. Thank you to everyone here in the audience and for those who joined us virtually on camera. I hope that you all learned something from George today that you can take home to your bench, your office, your team, or even your family as we approach the holidays. We rely on you to spread the word about science. We rely on you to counter the false narrative of science as a bad thing, or counter the narrative of vaccines. You're going home now to your loved ones over the holidays, and you have time. Talk to them about George. Talk to them about the woolly mammoth, and talk to them about the gene therapies that are coming out of this. Thank you for tuning in today, and I hope you'll join us for the next time when we tape The Dish. Thank you.